Hi everyone, and welcome back to the drawing board by TBPi. This week we're going to be looking over the method of undetermined coefficients for solving ordinary differential equations. The method for undetermined coefficients is basically the guess and check of differential equations. And it's just like what we talked about last week with linear homogeneous equations, except there's a little extra work involved. So last week we learned how to find complementary equations, which we'll call yc of x. And this week we'll have to start worrying about particular solutions. For these types of problems, you still find yc the same way that you would for a homogeneous equation, where you have some differential equation that's equal to 0. The difference now is that it's not equal to 0, but you still find your complementary equation as if it was equal to 0. The solution to these non-homogeneous equations, y of x, will be equal to the sum of these two equations, your particular solution and your complementary solution. And remember that you solve for your complementary solution as if it were a homogeneous equation, even though it isn't. Another important note about adding these two terms together is that you want to avoid any duplication between the terms. So for example, if one equation gives you some constant times x, and the other equation also gives you some constant times x, you don't want that showing up more than once because it's going to complicate your algebra. Like I said earlier, this method is basically just guessing and checking. So how do you know what to guess for y of p? Well, there's a couple rules of thumb depending on the type of problem that you have that can really help determine what y of p is. The first rule of thumb is for polynomials of order m. So let's say that, instead of your equation being equal to 0, it's equal to something like x to the 4th. This means that your y of p guess would start out as coefficient a times x to the 4th plus b times x cubed plus c times x squared all the way down to a constant term. Even if it's only x to the 4th, you always have to include every single power all the way down to 0. The second rule of thumb is for exponential terms, so e to the mx. Here, anytime you have one of these terms, your particular solution guess should start out as some constant coefficient times e to the mx. The most complicated rule of thumb is for any time you have trig functions like sine of x or cosine of x. In this case, whether or not you can just translate this down like we did here, where we just attached a coefficient to it, will depend on the orders of the derivatives involved. So for example, if you do have a y single prime in your equation, then you want to make sure that the y of p that you use is equal to the sum of these two terms. If there is no y prime, then you can usually get away with just matching the sine or cosine that you have in your equation. Another important thing to note here is that if this equation doesn't work within the context of the problem you're solving, something you can do is add an x to the front of, say, your a e to the x term or one of your sine or cosine terms, and that can usually fix whatever problem you're having. We'll see an example of that later in the video, and you'll see what I mean. Now that we've gone over the rules of thumb, we can look at our first example problem. In this particular problem, the only term that we have to worry about is this 8x to the 5th. Now you'll remember from the first rule of thumb that we want our particular solution to be written in terms of the largest power of x shown. In this case, that being x to the 5th. Now you'll also remember that even though we don't have lower powers of x included in this problem, we still need to include them in our particular solution. So if we're going to go ahead and write out our particular solution, we'll start with a x to the 5th plus b x to the fourth, and we're going to go all the way down until we are out of x terms. Since we're going to need to plug this equation in here, we're going to need all of these different levels of derivatives of this equation. Now, I'm not going to make you sit through me writing all of that, so through the power of editing, I will be back in a moment with all those written down. Now, we could go ahead and directly plug these things in and write out a big long equation, but that's going to take a lot of space, and there is an easier way to do it. Because we only have x to the fifth here, any terms that are attached to any lower powers need to sum to 0. Because the equations that we're dealing with are so long, I think it's easier to just look at the coefficients that we need to deal with for our different y's, apply them to these equations as they are, and then isolate terms based on the power of x associated with them. So starting with our original equation, up here we have -2 times y, so we need to multiply everything here by -2. For the first derivative, it's just -1. Same for the second and third derivatives. And the fourth derivative we get to leave alone because it doesn't have a coefficient. Now you can see how this might be useful for writing out equations to solve for all of these different parameters. This problem is unique in that we have 6 parameters we need to solve for, which is a pretty high number for these types of problems, but this is actually not as bad as it looks. So for starters, the only x to the fifth that we have in this entire equation is the one right here, the a x to the fifth term. Now we need to remember to multiply this by -2, so what we end up with is -2a needs to be equal to 8, so that we can end up with this 8 attached to the x to the fifth over here. Everything else is going to have to add up to 0. So next we'll take a look at our x to the fourth terms to get that equation. So from here we have -2b. From here we end up with -5a. And if you go any further, you don't have x to the fourth anymore. So we know that this equation needs to be equal to 0. We'll do the same thing for our x cubed terms. So here we have -2c. Down here we have -4b. And from here we have -20a. Once again, that's equal to 0. Move on to our x squared terms. We have -2d from right here. We have -3c. We have -12b. And we have -60a. Once again, that's 0 because there are no x squared terms in our solution. Now we can move on to just the x terms, where here we've got -2e. Here we have -2d. Here, -6c, -24b, and positive 120a. Finally, we'll go to our constant terms. We have -2f minus e minus 2d minus 6c plus 24b is also equal to 0. Now, if there were other terms here, like let's say we had plus 3x cubed, then the equation that we derived from adding up the x cubed terms would need to be equal to 3, not 0. But in this case, all of the equations except for the first one are equal to 0 because we don't have those powers of x represented in the initial equation we're given. I've gone ahead and rewritten all of those equations so that we can start solving for these coefficients. In this particular problem, it's really easy to just go down the line because every equation adds a new coefficient that we don't know the value of yet. So from this first equation, we just have to worry about a, and we can see pretty quickly that a is equal to -4. That means b, we now have -2b minus 4 times -5 is 0, which means that b is equal to 10. Now, we can go on and continue solving this algebraically, but in this particular instance, I would actually recommend using matrix math to solve for this, because we have 6 equations and 6 unknowns, it can get a little tedious to solve this by hand. So I'll be back in a second with the final answers written out. And if you want, you can check my algebra to make sure that I'm correct, but doing this using matrix math is much simpler. We now have the values of all of our coefficients, and again, I used matrix math to solve for these. We can go ahead and write our final form of our particular solution. So our particular solution is a, which is -4 times x to the 5th, plus b, which is 10 times x to the 4th, and so on. And this is the final answer for our particular solution. Remember that the true solutions for these problems are the sum of the particular solution and the solution that comes from the characteristic equation, which we covered in our homogeneous equations video. Now we can move on to another example problem that uses our second rule of thumb concerning exponential functions. So we already know from our rule of thumb that we want to try using a particular equation solution of some coefficient a times e to the 2x. Just like last time, now that we know the particular solution we're going to test, we need to take the appropriate number of derivatives. In this case, we need the second derivative, so we'll start by taking our first derivative, which is going to be 2a e to the 2x, and our second derivative of this particular solution is going to be 4a e to the 2x. Now we need to plug this in and make sure that we get something in the right form. So we have 4a e to the 2x here minus 4 times our particular solution, which is a e to the 2x, should be equal to 2e to the 2x. Well, you'll notice that these two terms are going to cancel, and it's impossible for this to be equal to 0. So that should tell us right away that this particular solution that we've chosen to test isn't going to work for this problem. So then the question becomes, if the rule of thumb doesn't work for this problem, how do we approach it? In most cases, when the rule of thumb doesn't work, the best thing that you can do is multiply the front of your particular solution by x, take the derivatives again, plug it in, and see if that works. So now we're going to try a particular solution of a times x e to the 2x. Keep in mind that even when you multiply by x, you still need to keep this power the same as this power, or else it for sure isn't going to work. Once again, we'll go ahead and we'll take the derivatives. So y prime, we're going to need to product rule this. So we'll start with a e to the 2x, and we'll need to add that to 2ax e to the 2x. And then we need to take our second derivative. The derivative of this term ends up being 2a e to the 2x plus, and once again, we're going to have to use the product rule here, so we'll start with 2a e to the 2x plus 4ax e to the 2x. Now that we have all the pieces that we need, we can go ahead and plug this back into our original equation to see if we get something in this form that we can then use. I've rewritten the parts of the particular solution that we need for this problem so that we have more space. Now we can go ahead and plug all of this in here. So for starters, we can lump these two terms together. So we have 4a e to the 2x plus 4ax e to the 2x. And then we can subtract 4 times this term, which is minus 4ax e to the 2x. And we should be able to get this to be equal to 2e to the 2x. Right away, you'll see that these terms can cancel with each other, and we are left with 4a e to the 2x needs to be equal to 2e to the 2x. And from this, we can also tell that a is going to be equal to 1/2. Now we know we have a working equation and a value of a, so we can go ahead and write our final version of the particular solution. So our particular solution is going to be this with the 1/2 plugged in. So it's 1/2 x e to the 2x. With that done, we can move on to our third example, which deals with the third rule of thumb that we were given. Keep in mind that this rule of thumb cares about whether or not you have odd numbered derivatives in your problem. In this case, we do have an odd numbered derivative present, which means that our particular solution needs to include both sine and cosine. If this term wasn't here, our particular solution could just be a times the cosine of x, and that would be perfectly fine. Since we know that we need to include both sine and cosine in our solution, we can start by writing that the particular solution that we want to test is a times the cosine of x plus b times the sine of x. Once again, we need all of our derivatives all the way up to second order, because that's what we have here, which gives us negative a sine of x plus b cosine of x, and our second derivative is going to be negative a cosine of x minus b sine of x. Just like before, we're going to plug this in where appropriate, and then make sure that we end up with 2 cosine x on this side. Now you can take the same approach that I did in the very first problem, where you just look at these equations and you multiply them by the correct terms. So we are going to go ahead and do that again here, instead of fully writing out this entire equation with these terms plugged in. So this gets multiplied by 3 because of that 3 right there. This one gets left alone, and this whole thing gets multiplied by negative 2. Now, just like before with the different powers of x, we need to collect our cosine terms and our sine terms together so that the coefficients can be set equal to the appropriate numbers. From here, we know that all of our cosine terms need to add up to 2, and all of our sine terms, since we don't have any, need to add up to 0. So we'll start with our cosine terms. So from this equation, we have negative 2a is attached to a cosine. From the next equation, we have b attached to a cosine. And from here, we have negative 3a attached to a cosine. Again, since all of these terms come from your cosines, this needs to be equal to 2 from right here. We'll need to do the same thing with our sine terms. So here we have negative 2b is attached to a sine term. From here we just have negative a. And then from down here we have negative 3b. And that is going to be equal to 0, again, because there are no sine terms in the original equation that we're given. So we have our 2 equations, 2 unknowns, so we can solve for our a's and our b's here. This becomes negative 5a plus b equals 2, and this becomes negative 5b minus a equals 0. I'm not going to walk you through the algebra of this, but a turns out to be negative 5 over 13, and b comes out to 1 over 13. Now that we know the values of a and b, we can go ahead and write the final form of our particular solution. So plug in a is negative 5 over 13 times the cosine of x plus 1 over 13 times the sine of x. We've now seen each of the rules of thumb independently, but what happens when you potentially need to use more than one? And how do you account for the complementary equation and making sure that there's no overlap? Well, for starters, with the rules of thumb, you can in fact just string them together. So in this case, we have, an e to the x term and we have a power of x term. We can just take those 2 rules of thumb and put them right next to each other and everything will be totally fine. Another thing to note is in previous problems, I haven't bothered solving for the characteristic equation and the complementary equations, but sometimes that is something you need to pay attention to. Now, I'm not going to walk you through how to do that because that's addressed in the video on linear homogeneous equations, but I will just go ahead and write out the complementary equation for this particular problem so you can see what I mean. So for this particular problem, the complementary equation is C1 plus C2x plus C3 e to the negative x. Based on our rules of thumb, we would initially assume that the particular solution we're dealing with here is going to be a e to the x for this term, and then our powers of x all the way down to a constant. But you can see right away that we have a constant here and an x term here matching up with these. So that's going to cause some issues when you go to write your final solution. So instead, what we can do to avoid this is multiply all of these terms by x squared to make sure that there aren't any duplicate powers of x in our particular solution and in our complementary solution. We don't need to worry about multiplying this term by x or even x squared because we already know that this term is directly analogous to this term. So we'll go ahead, multiply these by x squared, and get our new particular solution, which is going to be a e to the x plus b x to the fourth plus cx cubed plus dx squared. Now, just like always, we're going to go ahead and get the appropriate derivatives. I will be back in a second with all of those written down. All right, now that I have all of the derivatives written down, we can go ahead and pull our second derivative and our third derivative, since that's what we need in this particular equation. Using the second and third order derivatives that we solved for on the previous page, we can go ahead and write out what our full equation is here. So from our third order derivative, we have a e to the x plus 24bx plus 6c. And then for our second order derivative, we have a e to the x 12bx squared, 6cx, and 2d. From here, we'll approach this exactly the same as we do any other type of problem, where we need to make sure that the coefficients correspond to the correct terms on the right-hand side of the equation. We'll start with our e to the x term, since we only have two of them. We have 2a e to the x needs to be equal to 3e to the x, so 2a has to be 3. We'll move on to our x squared terms. In this case, it's just 12b is our only term attached to an x squared. And we know that this needs to be equal to 4. Everything else will be equal to 0 because we don't have lower powers of x. So for x alone, we have 24b and 6c. That's going to have to be equal to 0. And then we have our constants, 6c and 2d. Will also have to be equal to 0. From here, it's just some straightforward algebra, which will give you that a is equal to 3/2, b is 1/3, c is -8/6, and d is 4. Now we can go ahead and write the final form of our particular equation using these coefficients. Using these coefficients, our final particular equation becomes 3/2 e to the x plus 1/3 x to the fourth minus 8/6 x cubed plus 4x squared. This is the final form of our particular equation. And with that, we have covered the method of undetermined coefficients and how to solve various problems using it. This has been the Drawing Board by TBPi. Thanks for watching.